Okay. So our related rates. Oh, thanks. Are basically going to be these real-world scenarios that are going to be derived in terms of time. Okay, so the first thing that you want to write down about related rates is that they're derived in terms of time. So which variable do you think we're going to use in order to represent time?
T.
T. It's not going to be a crazy thing this time, but yep, we're going to use T. So everything is going to be d something dt every time we derive. Okay, you ready? I'm going to start off with a story problem. The first one, we'll come back to you. I'm going to start on the second one because I feel like it's more straightforward. We'll see. I don't know. We'll see how we go. Okay. So the first example that we're going to do is we've got this hot air balloon, okay, and it's rising straight up off of a field, and we have this rangefinder that happens to be 150 feet from the liftoff point. At the moment that the rangefinder's elevation angle is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. So we are going to find how fast the balloon is rising at that specific moment. Piece of cake?
Absolutely.
Absolutely. Okay. I was going to draw a picture, but the book already drew a picture. So here is our scenario. Okay. So you might want to draw this down. Okay. We have this balloon, and if you want to draw a balloon to the best of your ability, that would be good.
You want us to draw that little thing?
I would at least draw a triangle. Okay, we have this rangefinder that's some angle away. Okay, and the base of the triangle, because the rangefinder is always the same distance, is 150 feet away. Okay, so the other thing that we're kind of looking at is this height off of the ground. Okay. So the height off of the ground is never constant. It is constantly changing. So we are going to use a variable to represent something that always changes. Okay? So the first thing that we have to do is figure out what equation is going to analyze this situation. Okay? So let's start with the basics. What kind of shape do we have?
Triangle.
We have a triangle, and specifically a right triangle. Okay, so if we're trying to analyze a right triangle, and we're working with some specific angle, we'll call this angle theta. Okay, and we have an opposite side and an adjacent side involved.
Just like those tangent.
Okay, good. So you're thinking SOHCAHTOA, right? SOHCAHTOA. And we've got the opposite side and the adjacent side involved. Okay, so opposite and adjacent is your tangent. Okay, so the equation that we're going to be working with is the tangent of theta is equal to your opposite over adjacent. Okay, so the next thing that we're going to do is we're going to kind of fill out the information that is given to us in this story problem. Okay, so we have this hot air balloon that's rising. One thing that is staying the same is which piece of our triangle. So if I come back over here and relabel this, the what is? The adjacent, right? So our adjacent side, no matter what, is going to be 150, period. It never changes no matter what. Okay, we're going to say, do you guys mind if I use an H for the height of the balloon? Would that make sense to you? That's a balloon. It kind of looks bad. I bet I can do better. Perfect. Much better. Okay, so moving on from there. Okay, so it says, now, this piece right here is an important thing to understand. Okay, at the moment. Okay, so what we are going to do is we are going to talk about a specific moment as this hot air balloon is rising above the ground. Okay, so at this moment, we know that the angle is what? pi over 4. So we're going to say theta is going to be pi over 4. Notice I'm using a different color, and I'll explain that here in a second. Okay, and we are going to say, it also says that the angle is increasing at a rate of 0.4 radians. Okay, so think about this one for a second. We have an angle increasing at a rate. What is that? That sounded, what? How do you write a rate of change? Like what's the notation look like?
N over X.
Okay, you're thinking average rate of change. We want instantaneous rate of change. So we're thinking like instantaneous rates of change is like the, what'd you say? The derivative. How do you write the derivative with the angle? How do you write that notation? If we're deriving the angle, what is it going to look like? Nice. D theta over dt. So a rate of change is always going to be a d something over dt. And since we're working with the angle increasing, we use theta as the variable. Okay, the second thing we have to think about before we just write down the rate is this a positive or a negative number? Okay, they're not always going to say negative or positive. You have to figure that part out for yourself. It's possible for objects to deflate or get smaller. So in that scenario, you would have a rate that was decreasing, meaning a negative rate of change. But in our case, it's increasing, so therefore we know our value is positive, right? Okay, so that's going to be 0.14 radians per minute. Okay, and what are we looking for? It says, how fast is the balloon rising? So what are we looking for? Fast is referencing what? A speed, like a rate of change, right? Okay, so how are we going to say how fast is the balloon rising? Which variable are we using to represent that balloon's height? H, right? So we're looking for a rate of the height. So how do we write that notationally? dH dt, there you go, good. So we're looking for dH dt. Okay, T, and I'm going to put a question mark for that's what we're looking for. Okay, so at this point, I'm going to go back to my equation. And anything that stays the same no matter what, I'm going to plug in. So what is the one thing that never ever changes? Now 150, right? Okay, so I can say that my equation is the tangent theta of, let's say our opposite is now h over 150. Okay, so now what we're going to do is we are going to derive our equation so that we can find our rates of change. Okay, so working on the left-hand side, what is the derivative of tangent? Good, secant squared. So I would have secant squared theta. What do I have to put at the end of this? Good, d theta dt, because I just derived theta in terms of time. Okay, now how do I derive h over 150? Think of that maybe as 1 over 150 times h. So what's the derivative of 1 over 150h? That's kind of hard to say. Yeah, 1 over 150, right? You just lose the h because it's h to the first power. Does everybody follow that? And then what do I have to put at the end of this? dH dt, good. Nice. Okay, so now once I derived my equation, I am now going to put in my blue stuff, my when moment, into the equation so I can find my instantaneous rate of change. So I am going to plug in my given theta, pi over 4. We have our rate of change for our angle as 0.14. and we are still looking for dH dt. Okay, so we can use the calculator here. Let's go ahead and isolate this, and then we'll just type this all in as one sentence into the calculator. How do I get rid of the 1 over 150? Multiply by 150, good. So I'm just going to have 150 times 0.14, we'll scooch that to the front, times the secant squared of pi over 4. All right, let's see if we can figure out how to type this in the calculator. All right, so first thing that I have to do is check my mode. Okay, so which mode do I need to be in since we're working with a pi over 4? Good. Okay, so mode, I'm in radians. Okay, good. All right, so I have 150 times 0.14. Now, how do I write a secant squared? Because we don't have a secant button, so what are we going to use? 1 over cosine, good. And I'm going to go 1 divided by, and I'm going to put this in parentheses because I have to square it. Pi over 4. And I'm going to end that parenthesis all the way through and then square it. So it's squared outside. Typing it in, or this whole process? The typing in part or the whole process? Did anybody else get 42?
Secant squared is 1 over cosine.
Secant squared is 1 over, so you have to do, so secant is 1 over cosine, but since it's squared, you have to do 1 over cosine in parentheses, and then square. Yeah. All right, so we found a dH dt, which is 42, so that means that this balloon is rising at a rate of 42. We need to label this. Yeah, I don't know. I forget which. We gotta go back. So it is meters per minute. So you got to go back up to the original to figure out your units, and it's really important you label that correctly. How do we do?
Wow, man.
Pretty awesome. That was a lot of work. Okay, I have another question, and it's a little bit
easier.
Well, the opposite direction of that. But I think you guys are getting this. You got this. I believe in you.
I think that's negatory.
We'll keep doing this until it starts to sink. Lots of practice. We got it. Even if we have to do the homework together, then we'll do that together. Okay? I won't leave you alone. All right, you ready for the next question? All right, here we go. All right, so we have water running into a conical tank. Whoa. Good question. What's a conical tank? Like a cone, right? I don't know how to make a shape out of a cone. That looks actually kind of coney. There's a cone. Okay, so the conical tank is running, or the water is running into it. So this thing is filling up at a rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Got it? Piece of cake, right?
No.
All right, let's start with the basics. Let's talk about a conical tank. Okay, what is the shape that we are working with? It's a cone, right? Okay, so we're working with a cone. So we got to figure out like what the equation is of a cone. Like what are we working with? Volume, right? We're talking about volume, and I know that it's volume. Do you guys see this unit measurement right here at the end of my 9? This says 9 feet cubed per minute. So feet cubed is telling me that the volume is changing at a rate of 9 feet cubed per minute. So we're talking about the volume of a cone. Okay, so, all right, that's good. We're good. Anybody know the equation for the volume of a cube? I mean a cone.
Oh my gosh.
Sorry, my bad.
Figure it out pretty quick.
The cube is a different shape, isn't it? 1/3, is that right? Somebody Google it real fast. Are you sure it's 1/3? 1/3 pi r cubed?
It's either, yeah, cube times height.
Yeah, pi r squared.
1/3 pi r squared times height. There we go. Okay, so there's our equation. All right, let's pull out some information. Okay, so we have the volume, or the water, filling into the tank at a rate of 9 feet cubed per minute. So how would I label that? If it's a rate, what notation am I going to use? Rate of change is a rate of change for the 9 feet cubed per minute. D, is it a, what is it in terms of, what is feet cubed? What are we talking about? Volume. So it's a dV dt. Okay? And is it a positive 9 or a negative 9? Is this increasing or is it decreasing? Increasing. The tank is filling up. It's getting bigger. 9, we can label this, I don't know if that's necessary, but. Okay, the tank stands point down and has, okay, this is interesting. And I'm going to use a different color here. A height of 10, so I'm just going to say h of 10, and a base radius of 5. Radius of 5. So this is like the total dimensions of this cone. Okay, and the question says, how fast is the water level rising? Okay, stop. How fast is the water level rising? What are we looking for? The height, a rate of change of height, so how would I say that? dH dt, that's what we're looking for. Okay, when the water is 6 feet deep. So what is 6? Height equals 6. Okay, so this is, everything in blue is a when. This is an instantaneous piece. The green is the only thing that stays constant. Okay, so let me try to explain this by picture. This is my cone. How's it look? Looks pretty coney. Okay, so the height of this right here has a max height of 10. Okay, and we have a radius of 5. Okay, so this water is like filling up. Here's my water. Okay, and we're trying to figure out what it's changing at, specifically when the height is 6. Okay, does that make sense? Okay. All right, so we are going to go to our equation, and immediately we hit this little problem. Okay, so look at all the information that we have. We have a dV dt, we have a dH dt that we're looking for, we have an instantaneous height. Okay, all of those are H's and V's, but nothing is talking about R's, right? We have no rate of change of the radius. That's not a question. Nobody told us anything about that. Okay, so what I have to do is I have to go back to my equation and I have to rewrite it in terms of one variable. Which variable do I want it to be in terms of? In terms of h, because we're talking about h's, right? We're trying to find a dh dt. We've got a height of 6, so we want my volume to be in terms of height. Okay, so you ready for this? You see that green information? Yeah. Okay, would you agree that if we're working with this cone, no matter what, the height and the radius will always be proportional, no matter where the water is, right? It'll always be proportional. Okay, so what we're going to do is we're going to use the ratio of a given height and radius to use that proportionality and replace our R with an H term. Okay, So do you remember how to set up a proportion? Okay, so to set up a proportion, I'm going to use the two things I'm talking about. I'm going to compare my height to my radius.
Isn't it like if it's 1,
It's 2 over 1
Yeah.
over 4.
It's exactly like that. Okay, so we're going to have a height over a radius, okay, and we're going to set it equal to their corresponding values. So what is my height? 10. So that has to go on top with my h, and my radius is 5. Okay, so now what I can do is I can take this proportion and solve for r so that I can replace the r in my volume equation. Okay, so how would I solve for r on that proportion? Do you remember how to cross multiply? So we would have 10r is equal to 5h. Okay, and now how would you solve for r? Divide by 10. So would you agree that r is equal to 1/2 of h? Okay, so it's always going to be half of the height of h, right? I promise it will get easier and we're going to practice it together. I won't leave you. Okay, so now what I'm going to do is I'm going to take this r and I'm going to replace it with the r up in my volume equation. Okay, so I'm going to have the volume is equal to 1/3 pi, and now what am I going to plug into the r? 1/2 h, good. And then I have squared times h. Okay, and I'm just going to simplify that real quick so it looks nicer. What do I have to work with first to simplify this? The exponent, good. So what is 1/2 squared? 1/4, so I have 1/4. And then do you agree, can I go ahead and say that I would have h squared times that other h right there? Which makes h cubed. Okay. And then now I'll get rid of that parenthesis there. I can multiply the 1/3 and the 1/4 together. Okay, so that would make what? 1/12. Good. That's like the hardest part of this whole thing. That part.
And then you just plug in.
Okay, so now we have our volume, not yet. Our volume that's in terms of height. So this is our big equation. Now we have to go ahead and derive it so we can work with our rates of change. Okay, so you ready to derive this? Okay, what is the derivative of v? 1 dv dt, good. Okay. Now, what is the derivative of, let's see, we just have h as our variable. Remember, pi is a constant number. So I'm just going to multiply the 3 times the 1/12. So it is 3 times 1/12. 1/4. So I get 1/4 pi. What's my new h exponent? Squared. Good. And then what do I have to add? dh dt. Okay, so there's my derivative. Now what am I going to do? Plug in your stuff, right? Plug in the stuff that they gave to us. So I'm going to plug in, let's see, I have dv dt is 9. The h that's given is 6. And I'm looking for my dh dt. Okay, so I'm going to square 6, and 6 squared is 36. So I have 36 divided by 4, which is 9, right? So I have 9 equals 9 pi dh dt. Then you would divide by 9 pi. So would you agree that my dh dt is 1/pi? Okay, so that means that this water is increasing at a rate of 1/pi. We got to label this. What's going to be my increments here? Feet. Okay, now remember we're talking about a height. How do you label a height?
H.
Just a H, right? Wait, no, height. You almost sold me there. Yes, H.
Was that wrong?
Yeah. Feet. We're measuring it in feet. My height is feet. Okay, and then our time increment is in minutes. There we go. We're using H as the variable to represent our height.
That's what I'm saying.
Yeah, I was asking how are we going to label the height?
All right. Well, yeah.
Right? Okay, how'd you do on that one?
So I got it right.
That kind of makes sense. So if we did another question like it again, it might kind of sync. Okay, let's do a couple off the worksheet. Yes.
So deriving with this amount.
Okay, so wait, which step am I looking at? Am I going back to the blue?
Yeah. So
Okay.
you took the 3 and times it by the 12, or 12, right?
Times the 3, yes. And technically the pi is like, I'm technically doing 1/12 pi
Okay, it's not variable.
times 3. Yeah, it's not a variable, it's a constant, so I'm just leaving it there. So it's okay. All right, so I did not print this out, except for I have like a few of these.
Okay.
So I have like 3 of them. Grab Jake. So everybody else able to find it in their OneNotes? That's there.
So why does it?
Okay, so what we're going to do is we're just going to start this worksheet, and we're going to go through the questions that look scary to you, and then once you start to feel like you got this, then I'll let you finish it.
Which ones are the hardest?
I don't know, I haven't done all of them yet.
It says 10.2 on